We're going to look at part 1 of 4.5 here. So here's some Bellwork here that you can pause and go ahead and work through. All right, now that you have paused and tried to work through this, if you haven't, I definitely encourage you to do so. We're going to go ahead and expand this thing. So the first thing we need to do is make sure that we expand over this division, and I do that with subtraction. So we have ln x squared minus ln, and we have the square root here, and the square root is really the half power. So we have e to the third y, and that is all actually to the half power. Here we have the 2 that can come out front. So you have 2 ln x minus. Here we have the half power that can come out front because the half power is to both of these items inside. So we have 1/2, still parenthesis, ln e to the third y. This negative half actually will go to the e squared and the y, just like it did up here in the exponent. So when I split this multiplication up, 2 ln x minus 1/2 ln e to the third, this y also gets the minus half as well, ln y. So you think it's actually addition, which it is, because I can rewrite it ln e to the third plus ln y. However, they both get this negative half distributed. So this would be in parentheses negative 1/2, and you have to distribute this negative half. So that's why they're both subtraction. And then I need to bring out this 3. So you have 2 ln x minus 3/2 ln e minus 1/2 ln y. And then the last thing you have to notice here is that I have ln e right here. Ln e is just 1, so that cancels, and you're left with that negative 3/2. Okay, so today, 4.5, the first part, we're going to talk about exponential and logarithmic equations. So our goal here is to solve equations using properties of exponential and logarithmic functions. And I have remember here, but remember is just all the properties from 4.3 and 4.4 that we talked about with logarithms and exponentials, such as these properties we just use here on the Bellwork, combining or expanding over multiplication and division, rewriting. This is probably the most important thing to remember, is that log base a of b equals y, let's say. You rewrite this as a to the y equals b. This is the most important thing that you can know in this chapter for the test. If you don't know this on the test, you're going to struggle. Okay, I tell kids all the time, when in doubt, write it in the other form. Okay, that's one thing that you can do. So here, solve the exponential equation. Okay, so there's a few steps to solve. Step 1 would be isolate the exponential. Okay, that means just get it on one side, your exponential. 2, rewrite as a log, or you can take the log of some base of each side. And we'll see both of those examples here coming up. And then 3 is just solve. Okay. So here, my exponential, 5 to the x, is already isolated. If I take this and rewrite it as logarithmic, I'm going to say log base 5, so same base, of 125 equals x. So that's how we would rewrite that. And remember, this is saying 5 to what power is 125, which is exactly what this is saying. So 5 to what power is 125? That would be 3. And this is real basic here. Here you can see I have the same base on each side. There's a bunch of ways you can do this. If the bases are the same on both sides, your exponents have to be the same. But we can also use, instead of rewriting here, we can take the log of some base. So if I take the log of base 5 of this side and the log of base 5 of this side, because what I do to one side I have to do to the other, this looks like log base 5 of 5 to the 2x equals log base 5 of 5 to the x plus 1. And we should know that a log of base 5 and an exponential of base 5 cancel. So you get 2x equals x plus 1. Subtract x, you get x equals 1. Okay. Which, if you just look here, your bases are the same, so the exponents have to be the same. We get right down to there. Consider the exponential equation here. We're going to find the exact solution, and then we're going to estimate it. Okay, you notice here that my exponential is already isolated. So 3x plus 2 equals 7. I'm going to go ahead and rewrite this as logarithmic. So this is log base 3 of 7 equals x plus 2. So you take the base of your exponentials, the same base of your logarithm. Of is your equal part. And then remember, a logarithm finds an exponent. So that's why that is the exponent there. And then I just subtract 2. So log base 3, 7 minus 2 equals x. Now, when I put this into the calculator, you're not taking 7 minus 2. You're not taking log base 3 of 5. This 7 will actually be in the parentheses. And remember, your alpha window will get you the log of any base. So 3, 7 minus 2, which x is about negative 0.228. It says 6 decimal places. 752. Sorry, 756. Okay, so this over here is your exact. This is your estimated. Okay, solve the equation here. And on all these, I'm going to put exact and the estimated solution. Just know to watch whichever one the question may ask for. Okay, here I need to isolate this exponential, so I actually have to divide by 8 first. So then you get e to the 2x equals, this would reduce to 5/2. Your exponential is now isolated, so we can rewrite it as logarithmic, or you can just take the ln of both sides, because ln is the inverse of e to the x. So these two would cancel. You get 2x on this side equals ln of 5 over 2. And this is exactly just rewriting it. Okay, if you don't put the ln on both sides and you just rewrite it as logarithmic, this is what you get here. Okay, and the last step is multiply by half or divide by 2. So we have x equals 1/2 ln 5 over 2. And you could write it like this. You could say ln 5 over 2 over 2. But we don't usually like to put fractions within other fractions. So that's why I put this half out front. And then if I put this into the calculator and get an estimate, that's 0.5 ln 5 over 2. Which is about 0.458 to 3 decimals there. Okay, so make sure you know how to put these into the calculator. Okay, solve the equation here, algebraically and graphically. So we're going to look at both models here. So my exponential is already isolated here. So I'm going to go ahead and rewrite it as logarithmic. So that's ln 4 equals 3 minus 2x. Okay, again, going from this to this was on that remember part. You have to know how to do that. I'll subtract 3. So ln 4 minus 3 equals negative 2x. And then divide by negative 2. So you have ln 4 minus 3 over negative 2 equals x, which is about, let's see, ln 4 minus 3 all over negative 2. I have 0.8069. Okay, about that. So when we solve graphically, we're going to say y1 will equal this left side, 3 minus 2x. y2 would equal that right side. And you are going to find where they intersect. Okay, so if this is my graph, here's y4. Okay, and this thing, if you know your transformations here, this thing's going to go left 3. It's going to get flipped over the y-axis and horizontally compressed by 2. So let's see, this one. We'll do this one in red. This one was in green. So you should have something that probably looks like, I don't know, maybe it looks like this. It might be a little bit closer here. Okay, and then this point right here, if you second trace or calculate it on your calculator, it's 0.807 comma 4. That's the ordered pair. So this is the x value, and this is the y value of when this is the x value. Okay, so you're looking for that intersection there. Okay, here we have a kind of a quadratic type, and we can use u substitution to help us out on this. So if I let u equal e to the x, we usually go with this middle term here, and I rewrite this would be u squared minus u minus 6 equals 0. Okay, because power to a power you multiply, so 2 times the x is the 2x. Go ahead and factor this. So factors of 6 that subtract to 1 would be 3 and 2. Signs are different. The bigger one's negative, so plus u minus. And then you have u equals negative 2 and u equals 3. Go ahead and plug this back in for u. So you get e to the x equals negative 2 and e to the x equals 3. Now, in solving this, we have to rewrite it as logarithmic. It's exponential, so the inverse is ln. So we have ln of negative 2 equals x, and ln of 3 equals x. Now, if you remember about the domains of logarithms, you cannot have anything 0 or less in here. So this would actually create no solution. And this ln 3, which is about 1.099 is your only answer here. But we want to see this other answer here as well. Okay. Okay, here's another kind of almost quadratic one. If we look here across here, you should notice a greatest common factor. So I see x e to the x as a common factor. So x e to the x is going to get factored out. I'm left with 3 plus x equals 0. Now here I actually have 3 factors. Here's a factor, here's a factor, and here's a factor. And we're set equal to 0. So I'm going to say x equals 0, e to the x equals 0, and 3 plus x equals 0. And we'll solve each one of these. Well, this one's already solved. This one I need to rewrite as logarithmic. E is my base, so I have ln of 0 equals x. And remember, it can't be 0 or less, so this actually produces no solution. And then here we would subtract 3, so x equals negative 3 for my solution there. And then when I plug this in, each one of these x's would get one of those, and I could check my solution. Okay, here's one that I've added in, and these get a little bit tricky. So notice that my bases are not the same on each side, okay? And you can do this either way, but we're going to take the ln of, or not the ln, but the log of one of these bases. Now, I like to do the one with the most terms in the exponent, but if the terms are the same, it doesn't matter, okay? And I can actually do one of those over here, or I'll do it the other way. So this would be 5 to the x equals 4x plus 1. So I'll do it both ways here. So here I'm going to start with what I think is the easiest way. I'm going to take log of base 4 of both sides. So I have log base 4 of 5 to the x equals log base 4 of 4 to the x plus 1. Now on this one, your log base 4 and your 4 cancel. So you get x plus 1. Over here, nothing cancels, but this x comes out front. So you have x log base 4 of 5. Now you have x's on both sides, so you need to get your x's on one side. So here I have x log base 4 of 5 minus x equals 1. In order to solve for x, I have to go to these two down to 1. And the only way to do that is to factor out an x. So if I factor out an x, I get log base 4 of 5 minus 1 equals 1. And then I would divide by this log base 4 of 5 minus 1. So you get x equals 1 over log base 4 of 5 minus 1, which is about, and in order to compare these two, we're going to put it into a decimal. So log base 4 of 5 minus 1. So we're at 6.2126. Okay, now on this one, instead of taking log 4, let's say you just want to take log base 5 because it's on the left and that's what you want to do. Okay, so the process is very similar. So I have log base 5 of 5 to the x equals log base 5 of 4x plus 1. Now here your log base 5 and your exponential base 5 will cancel and you get x equals. Here you're going to bring down this exponent, but this exponent will be in parentheses. And this is why I try to cancel with the one with the most terms, because now I have to take this log and distribute into both of these terms. Okay, so we have x equals log base 5 4, with the x out front, because that x isn't in, it's not in with this. And then plus log base 5 4 times 1, which is the same thing. Now I repeat the same process. I get my x's on one side, so x minus x log base 5 of 4 equals log base 5 of 4. Factor out an x, so you get 1 minus log base 5 of 4 equals log base 5 of 4, and then you're going to divide by what's in those parentheses. So x equals log base 5 of 4 divided by 1 minus log base 5 of 4, which is about, it should be the same, but we'll just put it into the calculator, make sure we didn't make any mistakes. One minus, okay. And I did get the same thing, so 6.2126. Okay, so it doesn't matter which way you do this, especially if both sides have binomials up here at the top, just pick one and go with it, because you'd end up having to distribute in there. Okay, so solving logarithms is pretty similar. step 1 would be to isolate / condense your logs. Okay, if you have more, like here, we've got 2 logs on this side. We need to condense that. We need to combine those. Step 2, rewrite as exponential, or take both sides to the same base. And 3 would be solve. Okay, and we're going to see both of these, especially when we get into some word problems in 4.6 and 4.7. We're going to see both of those examples. Okay, so here I have a logarithm on this side, and I have 2 logarithms on this side. So I need to combine these two. It's addition, so that means we're going to multiply. So log of x minus 2 times x plus 3, log of x squared plus 1. Okay, so these two have logs on both sides. They are both base 10. So if I take each side to the base 10, exponential, those cancel. So here we have x squared plus 1 equals x minus 2, x plus 3. Okay, this is a quadratic, so I need to multiply this out, set it equal to 0, and then refactor or use quadratic formula. So you have x squared plus x minus 6, x squared plus 1. Your x squareds cancel. You have 1 equals x minus 6. If you add 6 to the other side, you get 7 equals x. Now, with logarithms, the value inside your logarithm, we kind of talked about already, has to be greater than 0. Okay, so if I plug this value back in, 7 squared is 49, plus 1, that's positive. 7 minus 2 is positive, and 7 plus 3, that's also positive. So all of those are positive, so that actually works. If you're solving a logarithmic equation, you have to make sure to check your answers. Okay, that's going to be very important moving through here. Solve each equation for x. Okay, so this is in logarithmic form. We're going to go ahead and rewrite it. This is isolated, so if we rewrite it exponential, that base is e. So this would be e to the 8 equals x. And if I put that into the calculator and estimate it, that would be about 2980.958. Okay. Here, again, we're already isolated this logarithm, so I'm going to rewrite it as exponential. So that's 2 to the 3. So 2 to the 3 equals this. So 25 minus x. 2 to the third is 8. So 8 equals 25 minus x. So if I add x, so plus x, it gets rid of that, and subtract 8. 25 minus 8 is 17, so x equals 17. Again, well, I forgot to plug this one up here back in, but ln of this big number, that's positive, so that's fine. And then 25 minus 17 is bigger than 0, so that one works. Okay, so don't forget to plug those in and double check. All right, example 9 here. Now here, my logarithm is not isolated. It's not by itself. I've got these things out here. So you need to move those to the other side. And don't add those. That's not 7 there. Okay, so follow your order of operations. We're going to subtract 4. 3 log 2x equals 12. Divide everything by 3. Log 2x equals 4. And then I can rewrite it as exponential. So this is a base 10 here. So we have 10 to the 4th equals 2x. 10 to the 4th is 10,000 equals 2x. So if I divide that by 2, I get x equals 5,000. And when I plug 5,000 in, 2 times 5,000, that's a positive number, so we're good. Okay, so algebraically and graphically, okay, we kind of looked at that with exponential. We'll look at that with logarithmic as well. So algebraically first, so I have 2 logs over here. I need to combine that with addition. So we have log of x plus 2, x minus 1 equals 1. So I'm going to multiply those. But I can go ahead and rewrite this as log or exponential. This is base 10. So 10 to the first equals, if I go ahead and multiply this out, this is x squared plus x minus 2. Okay, this is a quadratic. So set it equal to 0 and solve. 10 to the first is 10. But if I subtract 10 from both sides, 0 equals x squared plus x minus 12. So I need factors of 12 that subtract to 1. Signs are different. The bigger one's positive, so that's x plus 4, x minus 3. So x would be negative 4 and positive 3. When I go and check, negative 4 plus 2, that's a negative number, so this cannot work. And then 3 plus 2 is 5. 3 minus 1 is 2, so those are fine. Now, just like the exponential with graphing, I'm going to set the left side to y1. So y1 equals log of x plus 2 plus log x minus 1. And then y2 can be the right side, which is 1. Then when we go to graph these, okay, we have y equals 1, horizontal line right there. And then your log there of these, if I go to graph that, that's going to look something like, let me just graph it here. Let's see, log x plus 2 plus log x minus 1. So that's going to look something like this. Okay, and this intersection right here is actually 3, 1. Okay, and you can calculate that intersection on your graphing calculator. This is a great way to check your solutions to make sure that you're correct, or if it's a multiple choice test, this is a great, quick, and easy way to solve any sort of equation that you have. Especially not all equations are solved algebraically. Okay, solve the equation here. And this is one that is not solvable really graphically or algebraically. I have a logarithm, an x inside, and I have a quadratic here. So we could divide by 2, but then we have to get these x's on the same side. But then if I rewrite it, so say I have x squared over 2 equals ln x plus 2. If I rewrite this as exponential, that would be e to the x squared over 2 equals x plus 2. So I either have an x in the logarithm or an x in the exponential, and that just creates a huge headache because I can't get x all by itself or x's together. So this is a great way or a great equation for solving graphically. So you have y equals x squared, and then you have y2 would be 2 ln of x plus 2. So let me see if I can pull up my graphing calculator here so you can see what this would look like. So here we're going to graph on one side we'll have x squared, x squared. And then the other side, we had 2 ln of x plus 2. And if I graph that, there's my parabola, and there is my other curve. And we actually want the intersection of those. So if I hit second trace, it gets me to the calculate screen, and we want the intersection. Okay, so I just scroll over to where one of the intersections occurs. It says first curve, hit enter, second curve, enter, and then you can guess or you can just hit enter. And then it spits back, this is the x value, this is the y value. And I would do the exact same thing for this intersection over here. Okay, so one of the x values, so we had our graph look like this. So we have x squared was this one, and your logarithm was like something like this. So we have this intersection and this intersection. So one of the intersections was negative 0.712, comma 0.507. And the other intersection is 1.6, comma 2.562. Okay, and then so these right here, the x values are your actual solutions. Those are the ones that we're looking for. Okay, so I got some word problems here. So lake transparency. If I naught and I denote the intensity of light before and after going through a material, and x is the distance in feet the light travels in the material according to the Beer-Lambert law, where k is a constant depending on the type of material. So our first thing here is to solve for I. So I'm trying to solve for this variable right here. I'm going to get rid of this term, and in order to do that, I either divide by negative 1 over k, or that's the same as multiplying by negative k. Okay, so you have ln of I over I naught equals negative kx. Now, to get rid of ln, we're going to rewrite this as exponential. My base is e, so that's e to the negative kx equals I over I naught. And then we multiply by I naught. So I equals I naught e to the minus, this e doesn't go, so the 0 here is a subscript, e is a normal, and then you have your exponents of negative k to the negative kx. Okay, for a certain lake, k is 0.025. The light intensity is I naught equal 14 lumens. Find the light intensity at a depth of 20 feet. And distance, it says right here, is in feet. So that's good. I don't have to change that. So I equals I naught, which is 14, e to the negative 0.025 times x, which is 20 feet. And I just have to put all this into the calculator. So I have 14 e to the negative 0.025 times 20. And I get about 8.5 lumens. For that. Okay, so here we have some investment types of equations, and we had two equations for investments. It was A equals P 1 plus R over N T, and A equals PE to RT. Okay, this PE to the RT is compounded continuously, and it will actually say the word continuously if you're using this one, else you're going to use this one. So a sum of 5,000 is invested at an interest rate of 5% per month or per year. Find the time required for the money to double if the interest is compounded according to the following methods. So we're going to compound semi-annually. That means we're going to use this first formula. And I'm going from 5,000 and doubling it. So now I'm going to 10,000 equals 5,000, 1 plus R, which is 0.05. Semi-annually, so that's twice a year. And then 2 to the, looks like we're just doing 1 year. Or time, we're solving for time here, sorry. So that's 2t. Okay, so I'll divide by 5,000. That's 2 equals, and if I do this on the calculator, that's 1 plus 0.05 over 2. That would be 1.025 to the 2t. I'm going to rewrite this as logarithmic. So that's log of base 1.025 of 2 equals 2t, and then divide by 2. So time would be about of 2 divided by 2, about 14.04 years. Okay? If it compounded twice a year, you'd need to leave it in over 14 years to double your money. If it compounds continuously, that's this equation here. So we still want to end with 10,000. We start with 5,000. E to the R, which is 0.05 t. Okay, so a lot quicker here. So divide by 5,000, you get 2 equals e to 0.05 t. Rewrite it as logarithmic. So I have ln 2 equals 0.05 t. And then divide by 0.05. So t is about, so ln of 2 over 0.5. 13.86 years. Okay, and I think that's about 2.5 months or 2.5 years difference. Yeah, so it's not a huge difference there. In terms of talking 4 years to 14 years versus 13 years, that is actually, I think I was right with 2.5. Yeah, almost 3 months there difference. Okay, a sum of 1,000 is invested at an interest rate of 4% per year. Find the time required for the amount to grow to 4,000 if compounded continuously. Okay, so that's A equals PE to the RT equation. We're going to go from 1,000 E with our interest rate of 0.04 to 4,000. So divide by 1,000. So 4 equals e to the 0.04 t. Rewrite it as logarithmic. So ln 4 equals 0.04 t. And then divide by 0.04. So t equals ln 4 over 0.04, which is about 34.66 years. Okay, so 35 years to go from $1,000 to $4,000. Okay, so that is it for solving. And make sure that you know how to solve. If you need to find some other videos, if you need to come in and get some more practice, definitely do that and reach out if you are struggling, because this is going to be very important to know how to do moving forward. All right, thanks for watching.